Okay, welcome to this module. My name is Newton. Now we have a couple of demonstrations here set up for you, but before I show you the actual demonstrations, let me just give you a bit of background just to put everything in perspective. Now I said in the module there that the soil under our feet has a lot of biodiversity. The soil under our feet has more organisms, just one teaspoonful has more individual organisms than the population of the whole earth, the human population of the whole earth. So that just puts into perspective what we have underground. Unfortunately, it's usually, because it's out of sight, it's out of mind, but the organisms below ground do a lot of wonderful things for us. Now, I know some of them are pathogens, and that's what maybe most of us know them to do, but the vast majority of them actually do wonderful things for us, and some of them actually control some of those pathogens. So it's been called a black box because for a long time we didn't have good enough methods to identify the organisms below ground. So that's how the term black box was coined. But now we're getting more and more sophisticated. There are molecular methods now, or methods based on DNA, that we've been employing, and we're peering into that black box and slowly getting to identify more and more organisms underground. So it will take a while, but we're slowly peering away, trying to get to know more and more of them. And at the moment, only about 2-3%, or certainly less than 5% of the organisms below ground have been identified, as opposed to, let's say, more than 80% of the trees and animals above ground. So it's going to take a while, but as I say, with current methods, it's going to happen eventually. So although we don't see them, as I said, they do a lot of wonderful things for us. And some of the things, or some of the products and services that they offer us are, for example, nitrogen fixation. I think that's a very good example. Everybody knows, or a lot of people know about rhizobia fixing nitrogen in legumes. So nitrogen fixation is very important because nitrogen is one of the most limiting nutrients in agriculture, for crop production in particular. And yet the air that we breathe has a lot of nitrogen. It's just not in a form that plants or we can utilize. So it takes all microorganisms to convert that nitrogen into a form that the plants can then utilize, and then when we eat the plants, we get the protein from there. So nitrogen fixation is one example of a service that soil microorganisms do for us. Now, related to that is the mycorrhiza. Now, a lot of plants have mycorrhizal associations, and these are fungi. So with nitrogen fixation, those were bacteria, but now it's fungi. Now, the mycorrhiza don't fix phosphorus the way bacteria fix nitrogen. What the mycorrhiza do is they get inside plant roots, and in a way, because of that, the plant is then, it's like an extension of the plant root, although we can't actually see them. They're so tiny, we can't see them, but they're there. So it enables the plant to explore more soil volume compared to a plant that doesn't have mycorrhizal associations. So with that greater exploration, then you get more absorption of water and nutrients that are, particularly those nutrients that are not mobile in the soil, like phosphorus and zinc. So that's what mycorrhiza do, help us, or help the plants acquire phosphorus, just like rhizobia help the plants acquire nitrogen. But there's more things that soil organisms do, and I mentioned it before, and that is biological pest control. Now, remember that for a long time, for thousands of years, we didn't rely on chemicals the way we do now, or the way we have in the past 50 or 60 years. It all started, I think, after the Second World War. That's when we became more and more dependent on chemicals. But for thousands of years before that, we were relying more on biological processes, not chemical processes. So the nitrogen fixation, the just from so organic matter and so on. And again, in the past few years, our cropping systems have become more uniform. And so because of uniform crops, we're also losing a bit of biodiversity underground. Because with biodiversity above ground, you also get biodiversity below ground. But if it's the same crop, because what happens is each crop has certain organisms that associate with it or that they prefer. So if you have the same crop year after year, then it's the same organisms below ground that are encouraged to grow. Whereas if you have different crops, a diversified landscape, that means also diversified rooting systems and so on, and so you tend to get a diversified soil microbial flora or soil biology. So these are some of the things that have been happening, but fortunately in the last few years people have realized that going the chemical way is not the best way. So we're getting back now to biological processes. For example, zero tillage. What zero tillage does is it increases soil organic matter in two ways. One, the crop residues that you see on the surface, they eventually get converted into soil carbon. And the other way is that you get a reduced decomposition of those crop residues. And so what happens when you till the soil, you are aerating it. And when you aerate it, you are increasing the oxygen supply to the soil, but also mixing whatever organic matter is there with the soil a lot. And so you're getting greater decomposition or loss of that organic matter into carbon dioxide. Whereas under zero tillage, you get reduced decomposition and so reduced loss of organic carbon. Of course, also reduced loss through erosion and so on, but also less decomposition. So you're getting addition of organic materials, but also less loss of that organic materials. And I say that because most soil microorganisms especially, they use soil organic carbon as their source of food and energy for their metabolism. So a soil that doesn't have enough soil organic carbon won't support a vibrant soil microbial community. So the key to having a vibrant soil microbial community is to increase your soil organic carbon. And if you want a diversified microbial community, you have to also diversify the landscape, either by mixing or growing different crops at the same time, intercropping or relay cropping and so on, but just diversify the landscape. That way you get a more diversified underground as well. And the other thing that, of course, I alluded to it as well, that microorganisms do for us is nutrient cycling. So these crop residues we see here, they actually have nutrients in there, but those nutrients are in a form that cannot be utilized by plants. They are in organic combination. So it takes decomposition of these residues into their chemical constituents before plants can utilize them. So what we'll show you in this module are a couple of examples of some of these wonderful things that microorganisms do for us, or organisms in general do for us. One of them is earthworms helping in decomposing these crop residues. We have a demonstration in there. And the other one is nitrogen fixation, which is why we are here. Although the plants are very small, actually, we may not see what we're supposed to see, but there's a handout, there are a couple of handouts in there, or inserts in your program, that show what you're supposed to be seeing here. Okay, how many people use legume inoculants here? What do you grow? Peas, dry beans, lentil, okay. Do you use granular or peat inoculants? Okay, both. What do you use?
Same thing.
So you also grow peas and beans and stuff?
Peas,
No,
lentils,
not beans, or peas and lentils. Does anybody grow dry beans? Yeah? Do you apply fertilizer or do you inoculate?
Fertilizer.
Fertilizer, yeah. Okay. Okay, I'll come to the fertilizer part in a little bit. But first of all, let me just show you what nodulation patterns we get when we inoculate our peas, for example, or lentil, it doesn't matter, with either peat inoculant or granular inoculant. Now, these plants are a bit tiny here, so we may not see what we're supposed to see. But as I said, yeah, just check the handouts. I've summarized there what we're supposed to see. So what we're supposed to see is with peat inoculants, you get nodules mostly on the crown, around the crown, or around near the seed. Now, the reason for that is you are inoculating the seed, and when you plant that seed, the rhizobia are not very mobile in the soil. So the rhizobia are just around where that seed is. And so when the plant grows, then those roots, as they go out, they get in touch with the rhizobia, and the nodulation starts from there. So the main thing is the rhizobia are mostly where the seed is. And so most of the nodulation is around the crown. So that taproot and a few centimeters around there. Whereas for granular inoculants, you are inoculating the soil, not the seed. So the inoculant goes in the soil furrow. And because of that, so the seed then, when you plant your seed, as it grows, then it grows, the roots pass through patches of rhizobia and then get nodulated that way. So a couple of differences because of that. First of all, crown nodules form first, usually compared to lateral nodules. And that's because, as I said, with seed inoculation, the inoculant is right there already, and when the roots come out, they meet the inoculant and start forming nodules. So with peat inoculants, you tend to get nodules that form early around the crown. But also because they form early, they also senesce or die early, or they have a lifespan. Whereas for granular inoculants, granular inoculants tend to have not just lateral, but both crown nodules and lateral nodules. So some will form very quickly around the crown, and then others will form much later. And as I said, with the lateral nodules especially, because they form later, so they start fixing nitrogen a little bit later, but then they also die later, and so sustain the plant where maybe some of the earlier nodules have started senescing. So a very good combination is both crown nodules and lateral nodules. And by that I don't mean applying both peat inoculants and granular inoculants, because usually with granular inoculants you get both. But I'm not trying to say that you don't get good results with peat inoculants. Usually we did some trials in northern Alberta where I started working before I came here. What we found, we had three formulations: liquid inoculants, peat inoculants, and granular inoculant. So the liquid and the peat were applied to the seed, and the granular was, of course, applied to the seed furrow or to the soil. And we had one site was in Beaverlodge and another one was in Saskatoon. We collaborated with scientists in Saskatoon. Unfortunately, we had two different seasons. One season was very wet like this one, like maybe the way last week was, and very waterlogged conditions. So what we found in general was that when all the conditions are fine, there wasn't much difference between the different formulations. It was only when you had stress conditions like flooding or maybe drought or maybe acid soils, then we found that the granular inoculants tended to perform better than the other formulations. So there's actually a saying, they say that granular inoculants are often better but never worse than peat inoculants. So that's not to say that peat inoculants are not good, but a lot of times they'll perform the same, only that granular inoculants are often better, or they can withstand more conditions than the other formulations. Okay, so let me see whether we can find these two types of nodulation here, but if we can't, we have dug some bigger plants and they are over there. We'll see them later, but let me just see whether we can find any of those patterns there. At this stage of plant growth, it's a bit too early. So you should look for nodulation maybe about the time these plants start flowering. From flowering to flat pod stage, that's a good stage to look for nodulation. These are a bit too tiny here. They were seeded late, that's why they're small. But the other thing is, don't pull the plants with your hands, because then you just be stripping the nodules. You'll be leaving the nodules behind. So actually have to dig the whole plant out, excavate the root out, and then remove the soil, and that way you have a better look at the nodules. And you don't. Sometimes you have to, maybe depending on how heavy your soil is, you might have to have a bottle of water to squirt and clean the soil off. But usually you don't need to. You can actually see the nodules without having to wash the roots. Okay, I see some nodules there along the taproot. Okay, that's crown nodulation here, right there. And whereas here, they are more along the lateral roots. But there's crown nodulation right there.
So this was peat?
But this is actually granular. So remember, granular has both crown and laterals. But because they're tiny, so most of the lateral roots haven't started going out yet. So you're still starting with the crown, and later there'll be.
What kind of lentils?
What kind of lentils? There's information there. There's a variety, I forget. Yeah, the variety is written right there. I'm sorry? When was it seeded? End of May, something like. Where's Ken? Okay, Ken, when were these seeded? Sorry? May 24th. Yeah. Okay, so I'll dig out some peat plants here. Again, I see some nodules along the taproot there, and this is peat. So there isn't much of a difference now because, of course, the plants are tiny, and so the lateral roots are just beginning to go out. So what you're seeing under granular, as well as in peat, still a bit of just crown nodulation. But later, then you'll be getting more and more lateral nodules here compared to here. Okay, the other thing I wanted to show you here, which is why I asked about anybody who grows dry beans, is what happens when we apply nitrogen fertilizer. So as I said, because the nitrogen fixation process is an expensive process for the plant, if you apply nitrogen fertilizer, then the plant says, thank you very much. I won't have to form nodules. I won't have to fix nitrogen because that nitrogen is here, already here. So that's what happens here. That's what we're supposed to show. I'll dig up a few plants and see whether that's what happened, but we'll see. But it doesn't have to be just applied nitrogen. It can be residual nitrogen. So if you have a soil that is already high in nitrogen, or maybe you had fallow last year, or not very a dry year the previous year, where you didn't much of the nitrogen didn't get used, and so there's a lot of residual nitrogen that can affect nodulation. So you don't get necessarily zero nodulation. It depends on how much nitrogen you have in there. So you can just have reduced nodulation if the amounts of nitrogen there are sort of moderate, not very high. So I'll see if I can dig up a few plants and see whether there's any nodulation here. So in this treatment, we have a high nitrogen. We put in, I think, was it 100 or 90 pounds of nitrogen per acre here. This is granular inoculant, and that's peat, and then uninoculated. There actually are some nodules. Okay. So there are actually some nodules there, but what happens is with nitrogen fertilizer, you either get reduced nodulation or reduced nitrogen fixation, or both. So even if you have nodules there, it doesn't mean that they'll be fixing nitrogen. And that's the other thing I haven't mentioned. These nodules are a bit tiny, so we can't really crush them. But when you crush a nodule, you're supposed to see a pink color. When you see a pink color, that means there are nitrogen fixation or nitrogen fixing bacteria there at work. So there's actually a lot of nitrogen fixation going on if you see a pink color. If you see a dirty gray color, that means there's nothing happening there. Or even white, just white pass or something, then that means there's nothing happening there. So you usually get this gray color when the nodules start dying. But in the early stages, usually you're supposed to get very pink color. So it also depends on the strain of rhizobium that has actually formed those nodules. See, the soil already has some indigenous rhizobia, but some of them may not be very efficient at fixing nitrogen. That's why you are inoculating your plants, because you are giving them this strain of inoculant that the company actually tested and found it to be very good at fixing nitrogen. And that's the one that you want to form nodules. But if the nodules are formed by some of the indigenous rhizobia, well, some of them will be good, but others may not be very good. So just because you have nodulation doesn't mean that you have a lot of nitrogen fixation. That's, I think, a point I need to make. Any question?
If the granular inoculant extends the access to nutrients, does it also extend the days to harvest? The maturity period?
I'm not sure. I'm not sure about that. I guess you had the question. So because the granular inoculants, the nodules form later, do they extend the days to maturity? In theory, you could say they could, but I don't think there shouldn't be much of an effect. It's not like actual nitrogen fertilizer, which maybe you apply very late in the season, which can maybe prolong the vegetative stage of the plant. So it's a possibility. I'm not very sure, but it shouldn't be much of an effect.
Yeah. Anti-gallons occurred in research with chickpeas because chickpeas always want to hang on.
Yeah.
The anti-gallon Current did that study because chickpeas have a problem hanging on in the harvest time, and he actually did studies where he did just nitrogen versus inoculant. And his work basically showed exactly that the inoculant, the chickpeas will hang on all through the fall, and where if he just uses nitrogen, it'll actually shut the chickpeas off at a certain point, and they'll come in and they'll harvest them. So that's proven research for sure. Yep.
Anything else?
What about the amount of nodules? If you've got more nodule mass on a root, what are the residual effects on the next crop? Like, if you get more nodules, will you get more nitrogen for the next crop?
I don't know whether you heard the question. The question is, if you get more nodules, are you going to get more nitrogen carry over to the next crop? I think in theory they shouldn't be very much, because the nodules, as I said, have a certain lifespan. So, by the time the legume comes to pod filling stage, the nodules are shutting down, and so they're exporting all that nitrogen to the plant for the pod filling stage. So the nodules, the senescent nodules that are left behind, they will have some nitrogen, but not as much as if you had cut back that plant when the nodules were still very vibrant, very, very pink in color. Yeah.
The reason I'm asking the question, one thing we're noticing with chickpeas just have this massive nodules. It's so much more noticeable than peas and lentils. But the data, when you look at cropping rotations, crops after chickpeas tend not to do as well, and that may be more of a water issue, but chickpeas will just have a huge amount of nodules on them versus peas or lentils. That's why I'm asking the question.
Yeah. Okay. Yeah. I think that's just the genetic makeup of chickpeas versus lentils or peas. So, yeah. Anything else? Okay. Let's move over to that. Walk over and see those 2 tanks of soil that you see there. That's an earthworm demonstration. Earthworms at work. So you can walk in. What we did, this was 2 months ago. So we put soil in those tanks and put litter at the top of each tank. And on the tank, on the right-hand side, we also added earthworms. Whereas the one on the left-hand side, we didn't add any earthworms. So just see what difference you can see. There's a lot of soil mixing in the tank on the right, of course, compared to the tank on the left. So the residues in the tank on the right are getting mixed because of those earthworms, but at the same time, you also see soil barrows or pores. I took photographs of those tanks 2 days ago, and they are in your handout there. So that's one of the great things that earthworms do. They'll mix all this plant material, all these crop residues for us, and once they are properly mixed, that's the beginning of decomposition. And then the fungi and bacteria will keep on decomposing that plant material until you get the nitrogen and the phosphorus and the sulfur that is contained in these crop residues. So it all starts with these bigger animals in the soil, like earthworms, and then the chemical engineers, as they are called, then finish the process. And these are the bacteria and the fungi. So that's what I wanted to show you here. But because those plants were so tiny, we also had plants that were dug out from other trials around here. But even here, it's not. I'll see if we can find a big nodule that we can crush to show the pink coloration, but they are all very, very tiny nodules, actually. Yeah, there's an example of a nodule. I crushed one here. It's not very pink, so there is some fixation going on, but not as much. It's supposed to be pinker than that. But they're tiny, they're a bit difficult to crush, but you can try if you want.
So if they're not as pink, is there a diagnosis or an issue that the nodules aren't as fleshy pink inside?
Well, sometimes it may be just because they're. Oh. Is it on? Yeah. It might be because there's. Well, I'll just. I've mixed them up here. Okay. Which one is it? Which one is it? Is it that one? But anyhow, if they're not very pink, it might be just because they're still very young, so the rhizobia are still growing in there, or it might be because they are very old, so they are, yeah, the plant is shutting down the whole process. So, but if it's a good size and they're not very young, not very old, but they're still pink, it means the strain of rhizobium that formed that nodule is not a good fixer of nitrogen. Yeah, because each nodule is formed by one bacterium. So it just depends on which one got in there first. If it's a good fixer, you get pink nodules. If it's not, they won't be very pink. Yeah. Okay, lastly, let's walk over to the other side. Okay, this is a mycorrhiza demonstration. Actually, a colleague of mine from Swift Current was supposed to come for this part. She's the one who designed all this, but unfortunately she couldn't travel with all these restrictions that we have in government now. So, but anyway, unlike rhizobia or legume inoculants, we can't show any structures here. You don't see nodules with mycorrhiza. So to actually see the mycorrhiza, you have to slice the roots and then look at them under a microscope to actually see the mycorrhiza. So, but there's a handout there that she prepared. You can look at it later. But what she's trying to show you here is that different durum wheat varieties, have different abilities to form association with mycorrhiza. So, for example, there's by the way, the mycorrhiza inoculant that is available now is called Mike Pro. So this is a strong-filled durum wheat, uninoculated here, but inoculated with mycorrhiza there. So we're supposed to see, because this is supposed to be a very good mycorrhiza variety, we're supposed to see a visual difference here between that inoculated side and the uninoculated side. Unlike this variety here, Eurostar, again, those notes are in your handout, Eurostar doesn't form very good association with mycorrhiza, whereas the one at the end there also forms good associations. Now, one of the reasons we're not seeing much here could be because the plants are still young, but also it could be because there's a lot of residual phosphorus here already. So again, just like nitrogen fixation, if the soil has already enough phosphorus, then the mycorrhiza association won't do much to benefit the plant because the phosphorus is already there. But the other part we wanted to show here too is with a lentil crop, if you apply both mycorrhiza and rhizobium inoculant, can you get synergism? So certainly some experiments have shown that you actually get much of a boost when you inoculate a legume with mycorrhiza and a legume inoculant at the same time. And these mycorrhiza, they're not like somebody asked me yesterday that his soil has phosphorus which is tied very, what shall we say? It's like a fixed phosphorus. So mycorrhiza is not like the phosphorus solubilizing fungus. It doesn't work like that. Mycorrhiza want help in extracting that fixed phosphorus. What mycorrhiza does is, as I said, just aids the plant in exploring more of the soil volume than actually trying to solubilize the phosphorus that is in the soil. There are other fungus or fungi called P-solubilizing fungi that do that, like the one in Tag Team. Tag Team has a rhizobium inoculant and a phosphorus solubilizing fungus in there. Any question?
Have you guys done any biomass tests yet?
Chantel has at Swift Current, but this was just supposed to be a demonstration here. But
Has it been done here yet?
no, not yet. No, not these. No, these were just put here for demonstration. So we haven't done any biomass measurements. So Chantel has some results there. There's some graphs she has included in your handout that shows how different varieties of durum wheat respond to mycorrhiza. Anything else? Okay, what do you guys think about all these microbial products on the market? I think you saw some of them there, and the canola there. Now, whether they work or not, I don't know. But to me, the fact that people are now thinking about biology again instead of just relying on chemicals, I think that's a good thing. So, as I say, you can test them out on your farm because there are claims that they make. Now, whether these products work on your farm, it will depend because your conditions could be different. So, I think on a small scale, just have a patch of that product, adjacent to it, have another patch without that product and see what it does. But the important thing to me, as I say, is that people are thinking back to biology now instead of just relying on chemicals, and that's a good thing. So if these products are not good now, I think with more and more research, they'll become better and better. So I think that's a good sign that people are thinking about microbials instead of just relying on fertilizers. And by the way, I'm not anti-fertilizer. I think a good combination is both organic sources of nutrients and inorganic sources of nutrients. One of them completely is not good on either spectrum. So